welcome back, all of you. Let's move on with the program. I'm very happy to introduce our next speaker, Professor Dan Hammerstrom. Dan Hammerstrom will give a talk which is not only an invited talk in this open day that we have today, it is also a talk in the series that we call Halmstad Colloquium. Halmstad Colloquium is a series of distinguished speakers, typically once a month. Actually this month there will be two, so there will be one also next week. The topics of the talks in Halmstad Colloquium are are within the areas where we have strong research at the university, so embedded and intelligent systems. And Dan Hammerstrom, that we welcome today, is working as a program manager at DARPA, the Advanced Research Project Agency in Washington, D.C., working a lot with future technologies and many of the technologies that we have seen developed over the last 30 or 40 years actually come from DARPA, or ARPA as it was previously called. For example, the ARPANET, which you now know as the Internet. I mean, you couldn't think of a world without Internet, could you? It all started at DARPA with the ARPANET. Dan is a program manager there in the Microsystems Technology Office. He's also a professor in Portland State University, Portland, Oregon. He has been both in academia and industry since he graduated first from Stanford as a master and from University of Illinois at Urbana-Champaign as a PhD. He has worked, for example, at Intel in the beginning of the 80s as a microprocessor architect. He started his own company called Adaptive Solutions in 1988. They developed and sold a massively parallel architecture on a chip, probably the first really massively parallel architecture on a chip. That was 25 years ago. It was used for image processing, pattern recognition, and neural network emulation. Dan has, as a research interest, then of course, embedded parallel computing, but also exciting areas such as bio-inspired information engineering and nano architectures. His contributions to the field has been, of course, very much recognized. For example, he is a life fellow of the IEEE. We are happy also to have him here as a regular visitor. So since about 14 years back and so on, Dan has more or less every year come to visit us, sometimes for only a few days, sometimes for as long as 2 months. So this time he is here to give a talk at this conference, and we are happy to have you here. So please welcome Professor Dan Hammerstrom.
Thanks, Bethel. So I'm very grateful for the opportunity to be here. I'm grateful for the chance to have come to Halmstad these last 14 years. I'm also grateful that I don't have to give this talk in Swedish, and you should be too. As Bethel said, I'm at Portland State University. The way DARPA works is people come in, typically often from academia, but sometimes from industry and other government agencies. We're allowed to work for 4 years only, so you try to do as much as you can within the 4 years you're at the agency, and then you leave. And the agency continues to turn over, and that's one of the reasons that DARPA has, I think, been as successful as it has been. As Bethel mentions, it's been responsible for the basic technology for the internet, GPS, stealth technology, the list goes on and on of the various things that have come out of DARPA over the years. It's probably considered the foremost funding agency in Washington, D.C. And so it's, for me, it's a great privilege to be involved with DARPA. There are 6 technology offices at DARPA, each of them specializing in certain kinds of technologies or application domains. I happen to be in MTO, which is the Microsystems Technology Office. And we deal with, traditionally MTO has dealt with what people used to call gadgets, so small devices, nanoscale devices, sensors, et cetera. But more recently, we've been moving more into the area of systems, and also in understanding and figuring out what the government and the military should do with respect to integrated circuit design and fabrication, especially as Moore's Law starts to wind down, which it will over the next few years. The director of my office is Bob Colwell, who some of you may know was involved with the Ceres program as a I think, an advisor for a number of years as well. And I've known Bob for many years. He was Intel's chief architect for a number of years back in the 80s and 90s. So at MTO, we worry about Moore's Law, as I mentioned. Moore's Law is ending. It's not clear when exactly it will end. Most people feel that it's going to end for economic reasons. There'll come a point where the investment in the next new fab simply isn't going to pay for itself in terms of the added financial advantages of new chip technologies are going to give the company, and it will stop. And Gordon Moore always said it would stop due to financial reasons. Now, the physics is what's making it expensive, but the reality is economics are going to rule the final decision. So it may go. Intel is now fabricating 14 nanometer. They have plans to take themselves down to 7. And they talk about 5 nanometers. There are a huge number of problems that have to be solved to get down into those dimensions. So Moore's Law may stop at 7 nanometers in, say, 2020. It may go for one more iteration for 5 nanometers in 2022, but it is going to stop somewhere in that time frame. So those of us at DARPA, we worry about this because we're trying to look out ahead and what's going to be coming, or is there anything that will come after Moore's Law? And then how does the semiconductor industry deal with the fact that Moore's Law has ended? Companies like Intel have made most of their money off of what are called shrinks and compactions. A microprocessor comes out, it's on an aggressive process, they lose money on it. It costs them more to make it than to sell it, but over time the volume ramps up. They start to move the processor into denser technologies, and now they start making a lot of money off of it. So their whole business model is based on Moore's Law. The other thing that's happening is that power scaling has stopped. Those of you who've been around for a while, you know that clock rates were increasing rapidly during the 90s, and all of a sudden in the late 90s, around 2000, they stopped. So we've been at 3 gigahertz now for the last 12 or 13 years, and the main reason for that is that power scaling has stopped. So what I'm going to, in the DoD then, we have a huge number of applications that are embedded, and one of the big problems with embedded computing is the power constraints in the system. We have a term we use called SWAP, S-W-A-P, which really means space, weight, and power. Weight and power, or space and weight, tend not to be too big an issue except as they relate to the power requirements. And power ends up being a huge constraint. We have a number of applications where we simply can't do the computation on the vehicle or wherever this environment is running at the power levels that are available to that unit. And so we're very interested then in how to increase the power efficiency, given the fact that from an industrial perspective, power has stopped scaling. So I'm going to talk to you about 2 programs today. One of them is called Perfect, which is a power reduction program. Well, both of them deal with reducing power in embedded applications. The first one talks about taking existing technologies and trying to squeeze out the last remaining power improvements you can get out of it before Moore's Law ends. The second one, Upside, is really looking then way beyond and going beyond where we are today with traditional digital technology and looking at radical departures from how we're doing computing today. So Perfect is a program that was started last spring. It's actually not my program, it's run by a guy named Joe Cross, who's a program manager at DARPA. The goal is to take existing digital technology and try to squeeze power efficiency out of it. And Perfect looks at a number of areas. So it's got architecture, looking at ways in which architectures can be improved. The industry has already done a lot in that area. Looking at reducing the clock rate, so that means performance is going to have to come from other ways, and concurrency and parallelism. Multi-core systems are examples of architectures that allow us to improve the efficiency. Resilience, which I'll talk a little more in a moment, is actually an increasing problem, which I'll talk about in another slide. And the other possibility is looking at algorithms, for example, that minimize the data movement. So they may require more computations, but the data movement itself, moving data, say, back to memory and back onto a processor, can actually consume more power. And if you can do extra computations at lower power to save long-term communication, then that's a win. And then the program itself also talks about doing simulation. So there actually is no hardware development that's going to happen with Perfect. The goal of the program is 75 gigaflops per second per watt. Okay, and I've had a lot of people say to me, well, that's not so much. I mean, GPUs are doing 20 or 30 gigaflops per second per watt. However, this is for the total system, and it's sustained. So if you look at typical embedded processors today, based on Intel or ARM processors, they're operating roughly around 1 gigaflop per second per watt. So this is roughly a 75x improvement from where we are today over the next few years. Well, this sort of summarizes what I said earlier. Moore's law is ending. So we see that the number of transistors are still increasing, although, as I said, I think that will probably stop at 7 nanometers, maybe 5. However, relative performance has dropped off, and part of the reason for that is clock speed has dropped off. And clock speed has dropped off because Dennard scaling, those of you who are familiar with semiconductor devices, Dennard scaling is really what's allowed Moore's law to continue. Dennard scaling is where the dimensions of the device and the voltage levels and power all scale proportionately. Well, we couldn't scale the supply voltage down any further because we're getting near the threshold of the devices. So now voltage scaling has stopped, and subsequently Dennard scaling has stopped. So that's why you see here the clock speed has stopped. We're getting a little bit improvement in performance, but for the most part, performance improvement has stopped. We're seeing more cores on the chip, but if you think about it, the cores take a certain amount of power. Adding more cores doesn't actually reduce the power. Okay, the power efficiency remains very similar. I was looking in the paper, or on a research page recently, and I came across some numbers that were very interesting, and that is that the UNIVAC, one of the early UNIVAC machines back in the early 50s, executed 2,000 instructions per second and consumed 128 kilowatts. So it was getting roughly 0.02 instructions per watt. Okay. So we have now improved to the point where we're doing close to 10, soon to do 10 gigaflops per second per watt. So that's a trillion-fold increase in power efficiency basically over my lifetime, and Bertel's too. Okay. That's amazing. I mean, that's basically Moore's law in a nutshell. However, as I said, now we're starting to reach the point where we're not scaling any further. We need to be more creative in that respect. So as I said, Perfect is trying to increase the power efficiency by roughly 2 orders of magnitude. They're trying to look at architectural changes, and as those of you who are familiar with computer architecture, you know the manufacturers have already added a lot of features to the architectures to try to improve power efficiency, being able to shut down parts of the chip, for example, being able to run parts of the chip slower than other parts of the chip. What Perfect's trying to do is to continue those kinds of innovations and maybe expand on them a little bit further. One of the things that Perfect looks at is running the devices at near threshold voltage, and I'll talk about that on another slide. They're looking at heterogeneous architectures. So you could have if you have a lot of the silicon turned off, what's often known as dark silicon, you may have specialized cores that you turn on when you have a particular kind of computation you want to do, and that core may then perform that computation more efficiently than a general purpose core. So heterogeneous, I think, is going to be one of the big research areas, and definitely going to be a win in this particular, in these efforts. Usually this results in more parallelism, so you're trying to exercise concurrency to increase performance, but you also have to specialize the core to keep the power, to make sure that it's more power efficient than doing it on a regular core. I mentioned resiliency earlier. Resiliency is becoming an issue. VLSI has been incredibly reliable. We developed a whole bunch of these fault techniques back when we were building tube machines. Those extended into individual discrete transistor and small-scale integrated circuits. But these days, integrated circuits are extraordinarily reliable. But what's happening is we're moving down to smaller and smaller dimensions. The semiconductor industry is using a lot of tricks and techniques. Okay, they use something called a phase shift mask to try and compensate for the fact that the transistors, the features on the mask are now smaller dimensions than the wavelength of light, significantly smaller. So they sort of use the quantization effects you see in the light, they actually use phase shift mask to compensate for that. But the result of this is that transistor features are no longer fixed. They vary slightly. They fluctuate stochastically. This is true of the number of dopant atoms that exist in the FETs. They fluctuate. So now you see this very broad fluctuation in transistor behavior. So if you're a chip designer, then you're going to have to be very conservative because you don't know exactly how those transistors are going to work when in the final chip that gets shipped to a customer. So you have to be conservative and account for all these potential variations. A lot of people are saying, well, you know, we should just go ahead and be aggressive and then put in techniques, and we have all this silicon we're not using, put in techniques to maybe increase the resilience. And so there's a lot of research in looking at, you know, having two sets of instructions. These are the reliable instructions, and these are the not quite so reliable instructions. In many applications, you might be able to get by with not quite so reliable instructions. So you maybe inject small errors, you may be working at lower precision. A lot of sensor data, and this, as I said earlier, this accounts for a lot of the processing that we defense systems do and that DARPA is worried about. You don't need a lot of significance for processing some of the sensor data. You can operate at lower accuracy. You don't need double precision floating point. People use it because traditionally it's been free for the most part. Now as we move into power limitations, we have to start looking at things like approximate computing and, as I said, resiliency. As we move down into near threshold voltage, now we've added another variation to the transistors. Since not all of them are going to turn on and off at the exact same threshold, so now we need resiliency even further. And then just talk briefly, these are the, DARPA worries about a lot of things that the DoD does. Small unmanned vehicles are very important. Surveillance, trying to collect data is very important. But also we hope that these things actually these ideas and techniques find their way into industry eventually. So I mentioned earlier about near threshold voltage operation. If you look at a device, they typically today are operating about 1 volt. The threshold is somewhere around 0.35 volts. And what you do is you actually reduce the power supply down to the threshold. So the transistors are sort of off all the time, maybe slightly on. Some slightly on, some slightly off. And the reality is you get very efficient computation. It's slower, but that's where the concurrency comes in. So we add more parallel computing to compensate for the slowness. But the efficiency of the computation increases significantly. And this is a chart actually from Intel predicting what near threshold voltage operation would be at their projected 7 nanometer and 5 nanometer process. Notice they're a little more aggressive than the numbers I gave. So the perfect program then has a number of focus areas. It focuses on architecture. It's looking at concurrency and parallelism, which is a really key aspect of getting these low power architectures to work properly. Very concerned about resilience, making sure that we have reliable computation. Locality is where we're trying to keep the data local, trying to move it as rarely as we can. And then looking at new ways to do algorithms that may in fact lead to more efficient implementation. There's a program at DARPA called NeoVision 2. And what the NeoVision 2 did is it took a bunch of imaging applications and implemented them in traditional imaging algorithms, and then they used neural-inspired algorithms. And then they implemented both of those on an FPGA. And it turned out the neural-inspired algorithms gave an order of magnitude, sometimes more, power efficiency. So it's the same, computing the same thing, but doing it in a different way actually had a tremendous improvement in power efficiency, which is a big surprise. People actually didn't expect to see that big of an improvement. Well, that's an example then of how algorithms could have a significant change. There was an article in the New York Times a while back where people talked about Moore's law of algorithms, you know, that if people look at algorithms enough, they can double the speed every 2 years. I don't believe that. However, I do believe that algorithms have continual opportunity for improvement. And so I think more work needs to be put there as well. And as I mentioned earlier, that's one of the things when we start thinking about approximate data, approximate calculations, what have you, the algorithms become more important. Perfect then also has a simulation component, so there's no hardware that's going to be built. So there's one group that's building a simulator which will try out all these various ideas. And the simulators obviously will do estimated power calculation. And then there's another group who's creating a set of programs to run on the simulator. So the people who are actually doing the power architectures or near voltage, threshold voltage operation, they have to use somebody else's programs to benchmark their ideas, which is very important. And And here is a list. I won't go through the list, but these are the people that are, there's 17 performers, we call them, on the program today. And this is just a list that gives you an idea of the various things that are being looked at. There's 3D, here's 3D threshold computing, embedded algorithms for resilient framework, resilient calculations and algorithms, various kinds of power reduction, et cetera. So it's a very exciting program, and although it's not my program, I tend to be involved with it a little bit. Okay, so that's perfect. And that particular program, as I said, kicked off last spring, and it's a 4-year program. And it's one of the things about, I can't tell you how much money in these programs, that's considered sensitive, but what I can say is that DARPA puts a lot of money in programs like this. And it's one of the reasons that DARPA has been successful. Another thing about DARPA, which makes more sense in the program you're going to see now, is that the philosophy of DARPA is if all your programs are successful, you're not being aggressive enough. It doesn't mean you want them all to fail, but you need to have enough programs that are far out and risky enough that you have a certain failure rate. Otherwise, you're not looking at sufficiently radical technology. So Upside is my program, which I started last year. It kicked off in the spring. And it is a much more radical program. So it starts up where Perfect leaves off. So it's much further out, but its aim is also to reduce power, increase power efficiency. This 2-axis graph here sort of describes what I'm trying to do with Upside. What I've done is Upside, incidentally, although it's aimed at a wide range of sensor data, the program itself has been designed to work strictly on imaging. So it's looking at computer vision and image processing, which there's a huge amount of in DoD applications. And what I did is, instead of talking about instructions per second, I wanted to talk about a higher level computational abstraction. So here I'm going to use the term feature. So those of you who work in imaging, you can imagine 7x7 Gabor filters passed over all the pixels in an image, and those we'll call features. So what we really are talking about here is gigafeatures per second per watt. Okay. If you look at what's actually out there in terms of the computing that's being done today, you see that there's an asymptote, and there's actually a cost efficiency ceiling. Cost meaning commercial off-the-shelf hardware. And we can't go beyond it for all the reasons I mentioned earlier. Unfortunately, we have a lot of DoD applications where the power available on the platform, the amount of data that's being handled, and the complexity of the data analysis is way beyond where we're at. So the question is, how do we reach this? Well, if we look at how systems are currently built today, one thing we see is a large number of data abstractions, right? You start transistor level, you've got these poor little transistors that are being driven rail to rail. They're put together to create Boolean logic gates. They're put together to create functional units. Functional units create processors. And then you have several layers of software on top of all that, and you have layers of opportunities for inefficiency. Okay. These I won't go through. These are very similar, pretty much the same graph that I showed along with the Perfect program. Again, just pointing out that power scaling has basically stalled. So if we're looking at data something operating at the front end, we're taking sensor data in. The reality is we don't need to use a digital paradigm. We could conceivably use analog. The data is originally in an analog form. And furthermore, it's not particularly high precision. We certainly don't need double precision floating point for a lot of the front-end processing that we need the sensor data for. And what you find is when you're processing it digitally, you're using hundreds to thousands of operations to analyze these data. And as I said, you're going down through multiple levels of inefficiency. The question is there some way we can get around that? Can we bypass the digital abstraction? So the fundamental premise of the Upside program is basically, is there a computational abstraction that I can use a lot of places in an image processing pipeline? And can I map that abstraction onto some kind of physical hardware that is computing it directly via the physics of those devices? If we can do that, then we end up with a much more compact hierarchy. We're not going up through all the various digital levels. Okay. So using the physics to extract features is kind of what we're trying to do, although we're thinking more broadly. So the question is, what should such an abstraction look like? So for the Upside program, we've chosen an abstraction called inference, and we have something called an inference module. Now, inference can be defined in a number of ways, and it turns out we have several performers on the program. Each has their own definition of inference. But from a generic standpoint, inference is like this. And this is a communication channel model, but pattern recognition has the same basic idea. You have some original message. This is the pattern you're originally trying. This is the original meaning of the pattern you're looking at. Gets encoded, so it may be a character that's encoded into a set of lines. It may be noisy and it smudges on the character, for example. And somehow you read this character and you need to determine what the original message was it sent. So if you watch this often enough, you can estimate these probabilities just by collecting statistics. So inference is just saying, well, given that I received this particular data, or given that I've seen this particular pattern in a set of pixels, what's the most likely message that was originally sent, given that I know something about the noise in the channel and the probabilistic behavior of the messages? And the same is true. What's the actual feature that I'm looking at? Okay. So this is inference. The next observation is that you can actually approximate inference through using feedback associative networks. It's one aspect of neural net models. These are what are called attractor networks. This is a very simplified version. This is more or less what we call a Hopfield net. And there's a set of weights that determine how each of these little elements compute. And you can define an energy surface. And the energy surface then creates a profile or a topology based on how you set the weights. You start this thing in a certain state, and it goes into some attractor state or some energy minimum. All right. So what we're going to do is we're furthermore going to require that these things that they self-organize. It's very hard to program these things. You'd really rather have the situation where you present data to them and they self-organize around the data. And then you want to put them together into hierarchies. Okay. And furthermore, you want to use something called sparse distributed data representation, which I don't have a lot of time to go into, but it's a different way of representing data. Does it very efficiently and does it actually from a low power perspective, which is one of the objectives. So what you do is you put a bunch of emerging devices together, and I'll give an example of those in a minute. There's an array of them. You can use either current or voltage values. You can also use oscillatory networks. Coupled oscillations. They will then synchronize, the oscillations will synchronize, or they'll fall into an energy minimum, and that can be likened to an inference process. So I have some topological space that I've set up by virtue of how I set the weights. I let the energy minima be the target vectors. I put an input vector in, it just falls down into an energy minimum into the closest target vector, and you can show that under certain assumptions that's an inference process. It's basically a type of pattern recognition. So what does that buy you? Okay, well before I came to DARPA, I was involved in a program at Intel called the Non-Boolean Computing Project, which, if you think about it, for Intel, that's actually a big stretch. That entire company is based on Boolean abstractions, digital. But what we did is we developed some ideas for doing this kind of computation using something called spin-torque oscillators. These spin-torque oscillators can be coupled. The strengths of the coupling, which can be electrical or magnetic, are basically similar to the weights I showed you in the Hopfield, this little simple Hopfield net. And you can show that they do this kind of inference. So they'll operate over small fields, subset of a pixel array, and they look for features. So what we said is we're going to use a 10 gigapixel array. One of the things that one of the systems that we're used as an example, and one of the groups that's actually working on this project is a system called Argus, which is done at BAE Systems. And they build a giant image sensor out of several hundred cell phone imaging chips, and then they stitch the whole thing together, and they get this giant image. So we assumed then a 10 gigapixel array, that we had 7 by 7 Gabor edge finding with different orientations. There were 24 orientations. And we said, well, we're going to let an Intel Core i7 do it, and we're going to use just one core. And this thing with one core is roughly at a 10th of a gigaopt per second per watt. And it takes it 7,000 seconds to look at the edges for every pixel in this single frame of this image. And it consumes 460 kilojoules. It's a 60-watt chip. Okay. Now what we're going to do is we're going to take these, and this, of course, is done through simulation. People have actually built these spin-torque oscillators, but have not put them in configurations like this. But the Intel group actually assumed what the CMOS interfaces and everything that was required to run this thing would look like. So that was all factored into the estimate. And we said if we had a 10 by 10 array of these oscillators, so we could look at 10 by 10 sections of this image at a time. And remember, these things, you present the pixels, and it immediately converges to to the closest best match feature. Okay. So instead of executing a number of discrete instructions, it's a single computation, basically. So the compute time was very fast, but the thing that was important is that it was extremely low power. These things are operating at literally microwatts, so they're computing in picoseconds or nanoseconds at microwatts. So they're doing a fairly complex calculation. So after we analyzed the data, we looked at DARPA, what we do, we have workshops, we go out and talk to people working in the technology area, and from that, we write a proposal, a request for proposals, and we put objectives in that. And we use these objectives in the upside proposals. So we said, with the emerging devices, we want to be up here, and then we'll have an intermediate result, which will be CMOS, and we're going to put it here, okay? The emerging devices, then, what we said as an objective is 3 orders of magnitude improvement in throughput and 4 orders of magnitude improvement in power efficiency. That's 7 orders of magnitude. And then something slightly less than that for the CMOS. We figured these are stretch goals. No one's going to make these, but we'll get a lot of proposals with people trying to get close. And the reality is, almost all the proposals that we got, people said they could meet these objectives, and they had a fairly convincing analysis that, in fact, they could. So from that standpoint, we felt vindicated in putting these very high numbers. Now the reality is there are things like Amdahl's law, there's going to be digital components in the system, so there will be actual things getting in the way of, the total system isn't going to see this kind of power improvement. But if you're doing a lot of the feature extraction and features of features and some of the computation that's required in these, using this, that is a huge computational element of any kind of imaging system, and now basically you can do it for free, for the most part, from a power perspective. So the upside program is divided into 3 tasks. The first task is take an existing imaging application. So one of them is the Argus application that I mentioned earlier. So what Argus does, they have this gigapixel array. It's in a pod that gets mounted under a helicopter, and it flies around. And it's looking at the ground, and of course it's flying at maybe 20 or 30,000 feet, so it's looking at a 40 to 50 square kilometer region. And it's trying to identify anything that looks suspicious in that region. At the moment, they can identify and track about 60 elements, usually vehicles of one kind or another. And the Army, who they built this for, has said, well, that's a good start. We actually think there are several 100,000 objects in that kind of a space that we want you to identify. So there's no way they can get there. This thing has a couple kilowatts available to it. They're using all the latest FPGA and GPU calculations they can. So naturally, they're very interested in trying to use upside systems in this application space. So you start with an existing application, and you define your version of an inference module, so we kind of let them do the inference module they wanted, and now put it anywhere you can and redeploy this application. You could do it in the simulation initially, using this updated inference module. When you get done with that, then do a CMOS, analog mixed signal CMOS version of the inference module in a chip, and now build a test bed based on these modules. And show us that you're in fact getting the 4 orders of magnitude that we expect in power performance improvement with the CMOS, analog CMOS. And furthermore, show that you didn't lose any accuracy. In other words, you're doing your pipeline just as well as you were before. So we're not asking them to do better, just asking them to maintain the capabilities of the pipeline. And then the final task is now take some emerging device, and we've had a number of different devices that were proposed to us, and build an inference module out of it. So within the confines of this program, which is a 4-year program, there really isn't time, and the state of the art of these emerging devices just simply aren't there that we could have them do the entire application. But to show an inference module using these things, we think it's a reasonable thing to do. So this is the schedule. The program just kicked off last spring. Actually, the numbers up here have changed. So these are fiscal years, have changed slightly. So we're probably in the first quarter here. People have defined their imaging pipelines, they've defined their image abstractions, they're working on their simulation of their imaging application, they're defining their CMOS architecture, and they're demonstrating to us, getting ready to demonstrate us emerging device implementation. There are two phases. Now at DARPA, they often have something called a down select. So you have a whole bunch of people do the first part, and then you take the best one and squeeze them down for the second. But we chose not to do a down select. But there are two phases, mostly for managerial reasons. So in the second phase, then, they take their application and port it to a parallel processor array, because we want them to be able to use very high-resolution images at video rates. And then finally, they create a complete test bed using the CMOS device, and then benchmark an image, or excuse me, an inference module version of an emerging device-based circuit. And then, of course, one of the things, as exciting as emerging devices are, and I am very excited about them because DARPA, like a lot of research groups, we've been building these devices for a long time, and no one's ever really tried to put them in a system. A typical emerging device, someone creates it, they show it makes a NOR gate or something, and then they move on to the next device. And what we're trying to do is actually use these in a system. So that's a very important result, and hopefully the emerging device circuits will show that. But what we also would like to do is use the CMOS to actually create chips, and I'd like to be able to make these available. There are groups within the military that are used to taking sort of very early prototype silicon and doing something with it. But I have this notion in my head of something I call a field adaptable Bayesian array. So it's a new kind of FPGA that can be used basically in these sensor data processing applications, and can be applied in a lot of areas, not just in the vision component of systems. Now, one more. I have only a couple minutes left, so.
All right, please go ahead.
Okay. Before I do, the one thing I neglected to mention at the beginning, by the way, is that Moore's law means the end of CMOS scaling. And a big question everyone asks is, well, isn't there some other device out there that we could use? And so far, the device community has not found a device that is a replacement for the CMOS transistor. And in fact, they're pessimistic that they can do that. It's not to say there aren't computing devices available, and what Upside tries to do is leverage computing devices, but they're not general purpose switches like we see with CMOS. So CMOS is it. It stopped scaling. We're going to use it forever. It's a great technology. There is no replacement that would actually be a replacement switch for CMOS and continuous scaling. So the only alternative then is to look at other ways of doing computation, and that was one of the motivations for the Upside program. And one of the reasons, even though this is a very risky long-term program, one of the reasons DARPA is interested in it is it's one of the first to really try to leverage new kinds of devices in a reasonable computation. So I only have a little bit of time left, but think of this as a preview of coming attractions. So I'm in the process of putting together a new program, and if you look at signal processing pipelines, you see something like this. And those of you that have heard my talks here at the university for the last few years have seen this many times before. But this is a cartoon. Very few signal processing applications use all the various blocks, but the sort of canonical application would have a signal would be captured. It may be converted into digital, but it may remain in analog. There'll be some kind of front-end signal processing. Then you have several levels of feature extraction. And in the case of the imaging application that Upside uses, you have other things you do. This thing rides on a platform, so it's shaking, so you have motion compensation, and you have parallax, so the thing is flying around like this, and the perspective is slightly different, so you have to compensate for all of that, in addition to doing object recognition. The problem is, as we move back in here, the Upside program sort of stopped. Our intent was not to take it back into pattern recognition, but rather do the front-end processing. And the reality is, we still have a problem back in here. So, for example, the Argus system I mentioned earlier, say Upside is successful, and now the Army is seeing 100,000 objects being recognized at any one time. What do you do with them? How do you know which ones are suspicious, which ones you should look at? A human analyst simply can't handle a workload like that. So you're going to have some additional processing you're going to have to do on those objects. You don't necessarily have to do final decision making or classification, but you need to reduce the number that you pass on to the human analyst or the operator in some form or another. So the question is, are there new ways that we can approach this area as well? And here it's more complicated. There are a lot of algorithms out there. They work at various levels, some good, some bad, but I would say that there's still a lot of challenges left in this area, and the question is there anything DARPA should do? And that's what I'm trying to convince DARPA that they should do something there, and what I'm trying to convince them, I'll show in a moment. But this is an example. This is actually taken from Argus that I mentioned earlier. And what you want to be able to do, so it's not just a question of identifying objects. You have some objects moving, you have two white Toyota pickups that are right next to each other. That's suspicious. So now you want to recognize what we call scenarios. And this is true not only of imaging, this is true of a wide range of applications. For example, in cybersecurity, it used to be you could use various kinds of simple pattern match to determine when a virus is transferred or launched into your system. Now those are being encrypted. So the only way you're going to be able to tell is by the behavior of the system. So that's what we call scenario. Scenario recognition now is the new important area that we're looking at. So recognizing, doing all the upside stuff, and now recognizing the objects in some way, and then finally doing scenario recognition on those objects. So I was talking to a guy who's the chief scientist of the US Air Force, explaining this. And he used to be a data analyst, so he got very upset. He said, "Oh, you'll never replace the analyst." And he gave me this long lecture about why we'll never replace the analyst, because the analyst is doing so many important things that can't be automated. And I said, "Well, we're not trying to replace the analyst. We're trying to do a little better job in filtering the object and help the analyst do their job better." He said, "Oh, that's a great idea." So we're looking at a number of application spaces, but as most of you know here, I've always been drawn to the bio-inspired space. DARPA has off and on over the years toyed around with a number of different bio-inspired algorithms, and we're continuing to do so. There's a lot of work now moving into the area of modular or columnar algorithms, still based on the attractor model that I mentioned earlier. And one of the promoters of this is a guy named Jeff Hawkins, Jeff was the inventor of the Palm Pilot, and has founded a little company, Numenta, which is self-funded, I might add. And he's building a number of algorithms like this, but there are many other groups in the US that are starting to look at these. And there's also a very well-established deep learning community that is starting to move in these directions as well. I'm going to skip over this, but what we're looking at is building hierarchical structures. So deep learning, for example, makes extensive use of hierarchy. And also looking at ways in which these hierarchies, using sparse distributed representations, these hierarchies can be implemented on specialized computing hardware to give us very high speed, probably not using emerging devices as Upside is. This I like a lot. Some of you may know Gary Lynch and Rick Granger. They're both computational neuroscientists, but they had a book. The book is somewhat controversial, which we can talk about offline, but I love this statement because it really, I think, describes what we want to try and do with these algorithms in a hierarchical structure. So these things, what we want to do is capture a more complex structure of the data and then be able to do inference off of that structure. And we want to represent it in a way that's easy for us to use. So what Gary and Rick said is, well, the only difference between human beings and monkeys is we just have deeper pipelines. Okay. I don't know if that's true, but one of the things they point out is that we can these pipelines then talk about creating hierarchically grammatical elements, putting together the structure of data in a certain way to where at the end you have actually something like a grammar or some other kind of high order representation that you can use then to do inference over these data. So one of the problems I have at DARPA when I talk about this is, well, we had the Synapse program a few years ago, and Synapse promised a lot and didn't really deliver, and all that is true. So what I'm trying to do is promise very little and deliver more than I promise. But I use this to kind of keep the perspective. Intelligence is definitely measured in more than one variable, so this is a very simplistic model. But the general idea is there's no intelligence. Computing is about here, and I think we've done extremely well in computing. Moore's law has helped us a lot. The fact that we have computers that are 1,000 times faster than they were 10 years ago, I think, has made a huge difference. My goal is just to do better than we do now, something I call intelligent signal processing. But if we go out here, you have to go quite a ways before you find mammals. Mammals do a kind of cognition, which I call small c cognition. They're very smart. If you have cats or dogs, you know how smart mammals are. We don't know how to duplicate that. Synapse said, we're going to do the cat brain. Well, I don't think so. It's very complicated. And then humans are out even further in what I call big C cognition. We do language and we do problem solving and planning. I gave this talk a few weeks ago in Heidelberg, and one of the people said, well, he says, I think this is actually closer to here than it is down there. Yeah, I think he's right. I just ran out of room because of the text, but yeah, I think that's correct. And one of the problems with artificial intelligence is they basically tried to go from here all the way to here without solving any of the intermediate problems, of which there are a significant number. So the goal of the program, which I'm calling a cortical processor, and I'm trying to sell it to DARPA now, is basically to take the algorithms we know today and try to do a little bit better than what we do today. So I've had people in the deep learning community interested in this. I have people in the computational neuroscience community. So the hope is I can sell this to DARPA, and that will fill in the rest of that, or at least fill in more of that pipeline that I showed in the beginning of this section. So with that, I'm over a little bit, but I'll leave it at that. Mainly, through our analysis, we found that this is a very fertile area for new kinds of architectures. So you can continue to use traditional CMOS, but there are new kinds of ways. These algorithms lend themselves very well, especially the low precision aspects of them, to specialized architecture. And then, remember I mentioned in the perfect program this notion of heterogeneous processing. Well, this is a perfect example of what might make a great heterogeneous core. With that, I'll end. Thank you.
Many thanks, Dan. Are there any questions to Dan?
None.
Well, then I have a question.
Okay.
But there was one. Okay, yeah, please.
So I mean, you talked a lot about the end of Moore's law. Can you elaborate a little bit more on more than more?
You know, you have to refresh me. I think more than more is doing new kinds of devices, or is it just using Moore's law to do new kinds of architectures? I don't recall now.
So basically to increase the functionality. I mean, beyond just an increase in density of transistors, right? I mean, you have more, and you have more definitely.
Yeah, I mean, Upside tries to do that, and it tries to do it in a number of ways. One is obviously abandoning digital, leveraging the transistors that Moore's law gives us. Those of you that do analog design will probably argue that you're not going to be at the same density levels in analog that you're able to get with digital, but that's yet to be seen. But I think, in a way, I propose two ways of doing that today. One is the Upside program, and the other is using this cortical processor idea. And the cortical processor, what we're finding is it's not clear that analog is necessary. Analog is much more complicated. But in cortical algorithms, the big issue is communication, and there's no way you can communicate with analog. You've got to use some kind of packet or digital-based communication, even though the computation may be done in the analog domain. But there's so much communication going on that putting a computation in analog doesn't make a huge difference. But those are two examples, I think, of
I mean, are there also other, so to say, projects in this direction? I mean, other projects actually?
You mean other efforts at DARPA?
Yes, exactly.
At the moment, no. I'm the unconventional computing person at DARPA. I think that what they're trying to see is how well this goes, and hopefully bring in more people. This is one of the things that Bob Colwell has done, is added computer systems to MTO. DARPA, a few years back, on the previous DARPA director, Regina Dugan, got out of high-performance computing. So we completely got out of that whole effort. The Department of Energy now in the US handles all the supercomputing. And DARPA got out of it completely, but then everyone realized, well, we still do a huge amount of embedded computing, and so the focus has been on low-power embedded. Now, some of these ideas for low power will find their way into exascale as well, because power tends to be a problem for supercomputers too.
Okay, I think we need to finish there. So thank you very much, Dan. And here's a small present from the university.
Okay. There's one thing I did want to say. I have been, thank you. I have been coming. So I have been coming here for 14 years, and I have seen a remarkable change and transformation in this university in this time frame. I think you should all be very proud of what you've accomplished. I think it's truly amazing to me to see a university kind of start from a very small scale and get to where it has. So I'm delighted to be here, and I hope to continue to keep coming back. Thanks.
Thank you, Dan. You have really contributed a lot to this. Thank you.